Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, we've got another customer requested topic. Here it is. PWM Inputs and Outputs with Horner. Now, PWM signals should be understood by pretty much any control engineer because sooner or later we're going to have to deal with them. And as PLC programmers, it's much more common for us to deal with PWM outputs. It's much less common to deal with PWM inputs. But our question from the field that we're dealing with this week was, is Horner able to read PWM signals as inputs with their controller? So we're going to answer that question today. Sneak preview, the answer is yes. And we're going to cover both how to deal with PWM on an input side and an output side. So let's get rolling. Okay, we're going to start by answering the question, what is PWM and what is it used for? Which Horner controllers support PWM? We'll talk about creating PWM outputs in a Horner. What is the workflow to do that? It will also review the workflow for reading PWM inputs into a Horner, and there'll be plenty of demonstrations throughout. Here we go. Okay, so what is PWM? PWM stands for Pulse Width Modulation, and it is a digital technique for achieving analog-like control with a pulse train signal. So with a PWM pulse train signal, your signal amplitude is kept at a constant. So with most PLCs, like with a Horner, you're talking about 24 volt DC. Your signal frequency is also kept constant. So 1,000 hertz or 500 hertz or maybe even 10,000 hertz might be common frequencies of your PWM signal, although you would keep that constant for any one signal. And then what you would vary is the on time of that signal over the entire period. Okay, so in the picture to the right-hand side, you're looking at a pulse train which is on 50% of the time. So that exact pulse train would represent 50% duty cycle. And duty cycle, again, is described as a percentage of on time versus the total period. All right, so really effectively what you are transmitting when you're dealing with PWM is the duty cycle value, which is a value between 0 and 100%. That's really what you're communicating when you're talking about a PWM signal. So that's the signal, but what is it used for? Well, there's plenty of examples. So PWM can be used to control the amount of power that's delivered to a heating element for controlling heat, right? It could be used for positioning a PWM controlled valve. It could also control the speed of a DC motor. It could also be used as a control signal with some variable frequency drives as an alternative to an analog speed reference. Now, in a lot of these cases, PLC PWM outputs like those you'll find on a Horner are low voltage, low power signals, so you can't typically drive the device directly. There's usually some sort of interposing device. It may be something as simple as a solid state relay. It could be a motor drive, but most of the time you're going to have an interposing device. Okay, now which Horner controllers support PWM signals? Well, basically all of them. As long as they have high-speed outputs, as long as they have high-speed inputs, then they can do PWM on the output side and they can do PWM on the input side. Now, keep in mind that PWM outputs are much more common in various applications in machine control than PWM inputs would be. So we're going to show you how to do both, but you're going to use PWM out much more frequently. Okay, so how do we configure PWM outputs in a Horner controller? All right, well, let's take a look at the workflow. Basically, we're going to start in the hardware configuration under local I/O, and we're going to go to the high-speed outputs, all right, and we're going to select PWM for one of the two, or maybe both, of the high-speed outputs that are on your Horner controller. So you're going to select PWM for those. Now, if you want a default frequency or a default duty cycle for when the controller's in stop mode, or if you want to hold last state to the last frequency in the last duty cycle when the controller goes to stop mode, then you can configure those as well. In my example, I haven't done that. I've just let them go to 0 when the PLC/Horner is in stop mode. After you've done the configuration, next you're going to create a couple of variables. Okay, one variable will be your duty cycle variable. Another variable will be your frequency variable. Now you'll need to map those variables to the high-speed I/O table, and they'll be basically in AQ registers, and I'll show you which AQ registers here in a minute, but you're going to map those two variables to the appropriate AQ registers that are part of the high-speed I/O table. And then in your program, it's really just a matter of setting the frequency where you want it and leaving it there, like 1,000 for 1,000 hertz, for instance, and then setting your duty cycle value to where it needs to be at any given moment as you're controlling the actuator. From 0 to 100% is the end result you're looking for. Now let's take a look at that high-speed I/O table that I was just talking about, so you can figure out where in that table is the PWM output information that you're looking for. Now, the specific I/O table is going to vary by controller. So if you've got a Canvas or a Prime controller you're working with, this is the I/O table that you will be dealing with, okay? So you can see that the duty cycle for the first PWM is mapped to register AQ421, and the frequency for the first PWM is mapped to AQ423, and they're both unsigned double integers. Okay, and then you can see the formula that I put here on the screen that tells you, where do you set the value of your duty cycle, for instance, through AQ421, if you're talking about PWM number 1, to get the result of the duty cycle percentage that you're looking for. So as you can see there, you need to set that value so that when you divide it by 32,000 and multiply by 100, you'll end up with the duty cycle percentage that you're looking for. Now, it's much simpler to set your frequency because there's no math involved. You just set the frequency. So for the first PWM output, if you're talking about 1,000 hertz, you set AQ423 to 1,000 and you're good to go. Of course, all these values that I'm talking about here are for Canvas and Prime. If you're talking about the micro, then the AQ values or the AQ register numbers are much lower in the register table, as you can see here. Okay, so same math exactly, just different AQ registers we're dealing with there. So that's PWM outputs, all right? Next, let's take a look at how we configure to measure PWM inputs coming into a Horner controller, okay? So how do we do that? Well, it's also a high-speed counter function, but this time on the high-speed input side, okay? So we go back to the hardware configuration, and under the high-speed inputs, under type for one of the counters, and it doesn't matter whether it's 2-counter mode or 4-counter mode, depending on your controller, you just make sure that you set your type to pulse width measurement, all right? Now, you're going to want to set your mode to width high, 1 microsecond count, okay? Because you're interested in how long that signal is high. That's what's going to give you your typical PWM measurement, all right? So you'll have to set the mode to width high. And then you've got up to 4 different inputs that you can use for high-speed counting. So you'll just need to set the appropriate input, whether it's high-speed input 1, 2, 3, or 4. Okay, so once you've done that, very simple, then you've just got one variable to map from the high-speed I/O table. That is basically the accumulator, because you're going to monitor that accumulator and it's going to tell you in 1 microsecond counts how wide that pulse is, okay? And then in your logic, you're going to do a little bit of math, okay, to convert those counts into a width and then into a duty cycle as a percentage based on whatever frequency is being used by that particular PWM signal. All right, so now let's take a look at the detailed I/O table for Canvas and Prime. All right, so there you can see we've got our double integer values for potentially our 4 PWM inputs, or our pulse width measurement inputs, all right, are shown there on the screen, and they're double integers, as you can see. All right. And then there is our math down there below. So what we have to do to convert, this number of pulses that we're getting in that's telling us the width of the pulse, we're going to have to do a little bit of math to convert that to duty cycle as a percentage. We start with creating a frequency divider. Okay, so we're going to take a value of 10,000, divide that by our known PWM frequency. Now, what do I mean by known PWM frequency? Whenever you're receiving in a PWM signal, you have to be told what is the frequency that signal is coming in at. Okay, so it could be 1,000 hertz, it could be 10,000 hertz, whatever that number is. Could be 500 hertz, could be 100 hertz. But that has to be a known value that you're going to plug into a variable. And then based on that known frequency, you're going to calculate what I'm calling a frequency divider that you're going to use to directly calculate your duty cycle percentage. And we'll show you how we implemented that in the demonstration part of our show today. All right, so as you can see, that is the high-speed I/O table for Canvas and Prime. And just as before, we also have a high-speed I/O table for the Micro series, but we're talking about much lower AI numbers here in the case of the Micro. Now, when I say Canvas and Prime and when I say Micro, I'm not specifically saying an all-in-one controller. So for instance, this table for the Micro applies both to Micro OCS all-in-ones. It also applies to the Micro CPU 250 and Micro CPU 200. All right, so keep that in mind. All right, and when I talk about the Canvas I/O table, that also applies to the Canvas CPU 300 in addition to all the Canvas all-in-one controllers. Okay, so now we're going to get to the demonstration portion of our show today. I'm going to show you how to configure and do a little bit of programming for PWM inputs and outputs, and I'm going to use Canvas for our demonstration. Okay, here's my demonstration program. We're starting off in Cscape, and we're going to start out by taking a look at configuring PWM outputs. All right, so as I mentioned in the slides, we start with hardware configuration. Now this happens to be a Canvas model that I'm working with for the demonstration today. All right, we're going to go to the local I/O part of the configuration, and we're going to press the config button next to the I/O there and go to module setup. And for PWM outputs, we're going to go to the digital output section of our I/O configuration. Now, for my demonstration today, I am just using one PWM output, and that is physically wired to Q1 here with the Canvas. Okay. All right. And I have chosen not to set any defaults for the PWM signal. So I'm going to let the frequency and the duty cycle defaults just be 0, which means if the controller is in stop or idle mode, it's not going to be putting out a signal at all. So I have not chosen to have it go to a specific frequency and duty cycle or to hold last state. I just left those at their defaults. So literally checking this checkbox was the only configuration I had to do. Pretty simple. Okay, so the next thing I needed to do was I needed to map a variable, okay, to duty cycle and frequency. Okay, so let's take a look at my retain variables here, because this is where I chose to create a duty cycle variable, which is a double integer, unsigned, mapped to the appropriate location in the memory table, in the high-speed I/O table, AQ421 in this case. And then my frequency is mapped to AQ423. Okay, so those variables have been created. Okay, piece of cake. All right, so I've done my variable mapping. Now I need to do a little bit of logic, potentially, for setting up my PWM output. So, for instance, I'm going to be effectively transmitting a duty cycle value over PWM, which is from 0 to 100%. Okay, so I've got an internal variable that I call PWM output duty cycle. I've got it as a double integer in my program. Okay, and then I'm converting that to a real, and then that value, okay, oh, I'm sorry, I made a mistake here. This is actually the double integer value that I've just shown you as being mapped to the duty cycle. Okay, this is not my duty cycle percentage that I'm going to be controlling from. My duty cycle percentage I'm creating in this math expression here, where I'm executing that math equation that I showed you on the slide, where I take the duty cycle value, divide by 32,000 and multiply by 100 to get my percentage. Okay, so anyway, that's my math that I have to do here. And then I've created a screen for PWM out for the demonstration purposes, where I'm able to manually plug in this value here. Okay, calculate what my resulting duty cycle is, and then I can set my frequency just at a fixed value. So whether it's 1,000 hertz or 10,000 hertz or 500 hertz, I can just set that a constant value. And then my device, my Canvas controller, is going to output a PWM signal on its output. Okay, so that's really all that's required for this demo program I've got for you here that you can download. I do also, by the way, have a slider that you can use to set your PWM output from minimum to maximum, from 0 to 100%. And as you move that slider, you can see the value change in your duty cycle output double integer, to create that duty cycle percentage. Okay, so that is my duty cycle output. All right, let's go ahead and go to the bench. So before I show you how to configure PWM input, because most of the time you don't need to use PWM input in most applications, let's just go to the bench and take a look at what I have so far. Okay, here's the bench, and here is the Canvas 7 that I just showed you the Cscape program for, that is sending out the PWM signal. Now over here, I've also got a XL4 prime that I have configured to read in the PWM signal. We'll talk about the program for reading in PWM here in a minute. But let's start with looking at my demonstration here for the Canvas 7. So I've started off with a fixed frequency of 1,000 hertz. I could set that to whatever I want, 500 hertz, 10,000 hertz. 1,000 is a pretty typical number. Okay, so that's the number that's directly fed to AQ423 here. And then by varying the value in AQ421, I end up with a duty cycle. Now the value that's plugged in here is 16,000. And so by dividing that by 32,000 in logic, we're going to end up with a duty cycle of 50%. Now, is that what we see over here? Sure enough, it is. Okay, and I also have this slider. So as I adjust the frequency up, the PWM up, you can see the frequency doesn't change. I misspoke there. As I adjust the duty cycle up, you can see that follows nicely there. Okay, and then I can do the same thing as I move my way down. So we're effectively modifying the duty cycle, and then we're monitoring the result over here on the OCS XL4 prime side of things. Now, how did we need to configure and program the XL4 prime to be able to read in and measure a PWM signal? Well, I'm going to show you that next. I've fired up the program for the XL4 prime that is reading PWM inputs. And just like I mentioned before, we have to start with hardware configuration. Okay, so here's my XL4 prime. Again, I go to local I/O, click on the config button next to the I/O there, click on module setup. This time we're talking on the input side, the high-speed input side for configuration. Okay, so regardless of whether we're in 2-counter mode or 4-counter mode, it's the same. We go down here to our counters, and for one of the counters that we want to use for measuring pulse width, we select from our pull-down list pulse width measurement. Now, we definitely want to make sure that width high is what we are measuring. That's what is important in this application, because remember, duty cycle is the amount of on time divided by the total period. So we need to know the time that the pulse is high, okay? We pick which input we physically got it connected to. In my case, it's the first high-speed input. And then generally the disable and the latch function are available for pulse width measurement, but I can't imagine where you would want to use those. So I've just left those disabled. And really that's all there is to the configuration side. Again, very, very simple. Okay, now let's go take a look at our logic. What logic did we need? I'll go to my PWM routine here, and this is where we do our calculation of that frequency divider that I talked about, right? So we're going to be taking the value of 10,000, which is just a constant, dividing it by the number of 1 micro. We're going to be dividing it by the frequency, not the number of counts. We're going to be dividing it by the frequency of which the PWM signal is writing, okay? And that's going to give us a frequency divider. And then when we're looking to calculate our duty cycle percentage, it's a matter of taking the number of pulses that are coming in through the high-speed counter and dividing them by that frequency divider, and that gives us our duty cycle percentage. Now, the one step I forgot to show you was the mapping of the PWM counts, or the pulse width counts, in 1 microsecond increments. That is done in our program variable table. I believe I have that configured as a retained variable. Let's see here. I do not. I must have put it as a global. Okay, so let's go down to our global table here, and yep, sure enough, we have the internal variable I'm using here, which is mapped to the appropriate member of the high-speed I/O table, which in the case of Canvas and Prime is AI 401 for the first high-speed counter accumulator. Okay, so that's all there is to it. Now, from the standpoint of screen development, I did develop a screen for monitoring PWM in. Okay, so this is where I type in the known frequency for the signal, okay? So 1,000 if it's 1,000 hertz, 10,000 if it's 10,000 hertz, 500 if it's 500 hertz, that sort of thing. And then based on this known frequency and the number of counts it's getting back from the high-speed counter accumulator, it'll tell us accurately what the duty cycle is of the signal coming in. And you saw that happening there on the bench. Okay, so even though this isn't a common thing to do, if you ever need to monitor a PWM signal from an OCS controller, from a Horner controller of any kind, CPU or all-in-one, certainly you can do that, and I've just showed you how. That does it for our content for today. If you're interested in training, we've got 2 courses scheduled in the first quarter of 2026. Get to our website and sign up today. All right, we'd love to interact with you online to learn about your application, see where we can help you out. You can do that at hornerautomation.com. You can get to our YouTube channel, leave questions and comments on our videos, and we'd love to hear from you on LinkedIn as well. Now, I'm really excited because next week we are going to be covering a much anticipated addition to the OCS 360 capabilities. Now, OCS 360 is Horner's cloud service. Now, to date, we've told you about the telemetry capabilities, the dashboarding, the alarming, that sort of thing. Now, maybe you're not interested in dashboarding or alarming, but maybe you are interested in accessing your Horner controllers that are controlling your machines remotely for the purposes of troubleshooting or debugging or changing out programs, and you'd like to do that through a secure tunnel without any additional hardware. Well, that is a new service that's available a la carte from OCS 360. Now, if you are interested in telemetry, of course, you can use OCS 360 remote alongside the dashboarding and alongside the alarming, that sort of thing. So we're going to be covering this next week, so you don't want to miss it. If you haven't subscribed to our channel yet, don't hesitate to do so. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week when we talk OCS 360 remote, let's all get out there and do some good.